This is a hurricane, the greatest storm on Earth, seen from 22,000 miles in space. Today, with the help of the weather satellite, radar, and reconnaissance planes, we are better warned than ever before when hurricanes approach. People can prepare, but that is all.
Our research group is composed of physicists, engineers, chemists, and mathematicians. We don't predict the weather, we make it.
And now, everyone complains about the weather. There's an old saw about how everyone complains about the weather, but nobody ever does anything about it. That's not quite true. China Lake did a whole lot of things about the weather. Over the years, the folks at the station made rain to break droughts. They broke hurricanes, too, and they cleared away fog. They modified weather patterns to help impede enemy operations. They developed tools and techniques for measuring, modifying, mutating, and otherwise messing with clouds cold and warm, storms small and large, and fog and hail and even snow. People have tried to exercise at least some influence over the weather, well, pretty much forever. From dancing for rain to beseeching Poseidon or St. Elmo for fair winds and calm seas. As early as 1890, the U.S. government had funded studies of the potential of smoke and explosives to convince rain to fall. During the 1920s and 30s, both government and industry sponsored efforts to make rain and clear fog using dry ice and exotic smoke. And giant fires were lit to try to cause potentially deadly fogs to rain out. By the late 1940s, China Lake was in a prime position to take up the challenge. The station's unparalleled expertise in propellants and pyrotechnics and energetics in general, combined with its active and broad-based research program, and with its unique combination of military and laboratory assets, allowed the station to pursue and apply state-of-the-art techniques to the chemical compositions, the creation and dissemination methods, the hardware, the methodologies, and, perhaps most importantly, the empirical evaluation of weather modification. China Lake research in weather mod began not long after the war. By 1949, the station was experimenting with dry ice cloud seeding and investigating more advanced technologies. Mid-1950s studies of smoke generation for battlefield screening and research into aerosol spray techniques for screening smokes led the station to develop a new method of silver iodide production and to begin new research in weather phenomena and modification techniques and technologies. In the early 60s, under Project ACE, the atmospheric control experiment, the station began active research in cloud physics and development of new weather modification hardware and techniques, resulting in the creation of advanced catalyst formulations and of ordnance quality catalyst generators, devices that were safe, reliable, and economically producible. And by the end of 1961, China Lake's Cyclops seeding devices were being used in hurricane-busting operations, leading to their extensive use in Project Stormfury. The station's program expanded quickly. China Lake weather modification efforts covered the full RDT&E spectrum, from basic research in atmospheric composition and dynamics, through hardware development and field operations support. Over the next decade, China Lake pursued weather projects around the nation, indeed around the world. And for all their impact, few people ever heard of those projects. Aside from place names like Dakota and Skagit and Project Santa Barbara, there were the obvious monikers like Stormfury and Foggy Cloud, the somewhat less obvious like Thunderbird and Cyclops, and the downright obscure like Grommet and Electo, and the ultimately secret Popeye. Many of these were operationally and politically complicated efforts. Most were conducted with other Navy and DoD activities, as well as various contractors, universities, and state and federal agencies, from the FAA to the State Department. After hurricane busting in Stormfury, China Lake's cold cloud modification subsystem was used effectively to support naval operations from Alaska to Antarctica. The station's focus was on supporting operational requirements. However, with Project Grommet, China Lake was able to break a severe drought plaguing the Philippines. And between 1967 and 72, the center also sent weather expeditions to India, Midway, Okinawa, and the Azores to seed clouds and train local people to do so for themselves. During the late 60s and early 70s, foggy cloud operations demonstrated fog clearing for airports and military operations. And other projects helped to suppress hail, increase snowpacks, and fill reservoirs. While the Philippine rainmaking effort had been a highly publicized success, there was another rainfall augmentation operation being conducted. One that didn't get a lot of publicity, at least not then. At a time when even the mention of military application and weather modification in the same sentence was classified, China Lake was tasked by DoD to try to extend the monsoon season in parts of Southeast Asia in an attempt to interfere with troop and supply movement on the Ho Chi Minh Trail. Project Popeye added a new dimension to the station's operational support repertoire and a new legitimacy to the concept of geophysical warfare. Cloud seeding is probably the best known aspect of WeatherMod, and the most obvious, but the station's research also included related efforts not centered in the clouds. China Lake designed and fired meteorological sounding rockets. EOLUS and ROCKAWS investigated atmospheric composition, temperature curves, and ozone densities. The station studied winds aloft and odd atmospheric phenomena, and pursued the characterization and detection of clear air turbulence, with an eye toward mitigation of that potentially deadly occurrence. Although military research in WeatherMod was eliminated in the mid-1970s by politics and treaties, the civilian sector continues to use techniques and hardware developed and refined by China Lake in hurricane abatement, drought relief, and fog dispersal. Technologies and methodologies pioneered by China Lake for WeatherMod and atmospheric control did find later application in modeling and simulation, tailored pyrotechnics, and advanced countermeasures. And its early contribution to geophysical combat was far from the lake's only foray into very unconventional warfare. But that's another story.
It has long been the hope of mariner and landlubber alike to in some way abate the fury of storms so that the safety of our ships at sea and our people ashore could be in some measure increased. The recent discovery at the Naval Ordnance Test Station now holds forth the hope of being able to ameliorate violent storms. The story you are about to see describes the first large-scale attack ever mounted upon a hurricane. The hurricanes that each year sweep upon our Atlantic and Gulf coasts carry with them the destructive power of many hydrogen bombs. These hurricanes spawn in the tropics and move at first westward and then northward along a gradually curving track. They move at a velocity of about 10 to 15 knots. The hurricane itself consists of a giant whirling wind circulating about a very calm eye in which there is essentially no wind blowing. Spiraling outward from this eye are gigantic spiral rain bands that very much resemble the arms of a spiral nebula. Seen in cross-section, one would find beneath each of these spiral rain bands a cumulus cloud tower sucking the warm, moist air of the sea upwards and expelling it in a gigantic outflow shield which may extend for perhaps 1,000 miles or more in front of the hurricane. The findings of the National Hurricane Research Project over the past 5 years has revealed, however, that the majority of the air sucked upward from the sea and extruded into the outflow shield moves through a single large convective cell or chimney located in the right forward quadrant of the hurricane. Now, it is in this portion of the storm that the Weather Bureau experts feel that the hope and the possibility for the modification of hurricanes lies.
Scientists at the Naval Ordnance Test Station, China Lake, California, and in the United States Weather Bureau, Washington, D.C., have conducted a preliminary experiment which may have long-term effects on hurricane control. As Knott's chemists were seeking a colored smoke which would be visible at high altitudes, they discovered that pyrotechnic and propellant compositions could be made which give high yields of silver iodide. They immediately recognized that this discovery could be applied to cloud seeding experiments. It was suggested to the Weather Bureau that this concept be used in the 1961 Hurricane Control Project. The Weather Bureau agreed. For this application, a propellant composition, Argentisol 5052, was developed. Essentially, it is a nitrosol propellant with silver iodate as the oxidizer. The initial formulation consisted of 70% silver iodate and 30% nitrosol binder. Silver iodate is normally available in 1-ounce quantities. Until a commercial supplier could be located, it was necessary to prepare the silver iodate crystals at Knott's. All the initial formulation and tests were conducted by the Research Department's propellant facility, which prepared 400 pounds of silver iodate in the required crystal size for large-scale testing. The oxidizer is blended with the rest of the propellant ingredients. The viscous mixture is then poured into casting molds, where it is baked at 130 degrees Fahrenheit until turned into a solid. A bomb-like container was designed and fabricated at Knott's. 2 seconds after it is released, cutters cut through the nylon cord, and the tail section falls away. As it falls, it releases and opens the parachute, which actuates the fuse and causes the generator to start operation. The propellant is cast as an end-burning grain with an axial inhibited hole formed by a micarta tube. The motor is designed to burn at 75 to 100 psi for 160 seconds and operate at altitudes up to 45,000 feet. Strands of magnesium Teflon Viton are used as a sustainer material, and aluminum potassium perchlorate, PMVT, as a first fire on the end of the propellant grain and as a coating on a disc of aluminum screen wire. The hardware design requires that ignition be transferred from the front end of the motor through a 12-inch long micarta tube to the nozzle end to fire the igniter. The ignition train consists of a fuse, which ignites an aluminum screen wire cylinder coated with aluminum potassium perchlorate PMVT. This transfers the ignition to the nozzle end igniter and fires the propellant grain. The first test was a failure. Silver iodide condensed inside the container. The reaction wasn't hot enough to completely vaporize it. Heat of combustion was raised from 650 to 900 calories per gram by adding 5% aluminum. The mixture on the left has the aluminum. August 24, the new mixture was tested in a container. It was a complete success at ambient temperature. An A3D with an internal bomb bay capable of traveling at the desired speed of Mach 0.8 in excess of 40,000 feet altitude was chosen as the aircraft to carry out the experiments. An adapter was fabricated by Knott's Naval Air Facility and installed in the bomb bay. It can carry 9 of the bombs. Knott's Naval Air Facility selected a bombardier navigator to follow through the experiments. August 29, the first live test was held 40,000 feet above the G1 test range at Knott's.
Minus 30 seconds. To right, minus 2 degrees. Minus 50. Stand by 10. Mark 1. Stand by 5. 5, 4, 3, 2, 1, 0. 1-4,
This test failed because the fuse wasn't adequate to transfer energy to the igniter at 40,000 feet. Igniting a propellant at that altitude is extremely difficult because of low atmospheric pressure and severe cold. The fuse was stepped up from 500 to 1,250 calories per gram at the transfer point by adding 0.5 grams of aluminum potassium perchlorate. A bomb with the new mixture was cooled down to minus 65 degrees Fahrenheit and tested in the high-altitude chamber September 7. It passed the test at a simulated 50,000 feet. The next live test was held September 11.
Stand by 10. Mark 1. Stand by 5. 5, 4, 3, 2, 1, 0. 1-4, you look like a good shape. 650, the same procedure as last time, back in the item at this time. Come back and join on you.
3 more successful drops completed the testing at Knott's. The next drop will take place in the wild turbulence of a hurricane. September 14, Knott's scientists and the bombardier navigator met in Miami, Florida, with the Weather Bureau's Deputy Director of Meteorological Research, Severe Storms, the officer in charge, Fleet Weather Facility, and officers from Hat Wing 1 and Hatron 11, as well as the pilot from VAH 11 who would fly the A-3D into the hurricane. Final details of the attack were coordinated that day by the various military and civilian agencies involved. September 15, NOTS and Weather Bureau scientists arrived at San Juan, Puerto Rico, just as Hurricane Esther was forming. The staging area for the experiment was Roosevelt Roads Naval Station, Puerto Rico. Roosevelt Roads Weather Station, which had received very early warning of Hurricane Esther from the Tyros weather satellite, maintained careful watch on her. On September 16, the hurricane was 400 miles off the Puerto Rican coast at latitude 23 degrees 30 minutes, longitude 60 degrees 0 minutes. The Hurricane Reconnaissance Squadron, VW-4, sent a control ship into the storm to guide the A-3D to the drop point. The Weather Bureau sent a B-57, 2 DC-6s, and a B-26 into Esther to record and observe. The Air Force sent a U-2 on a photographic mission. Esther had the typical spiral rain bands which encircled and converged upon her eye. The cloud floor of the eye had the swirly pattern of small cumulus and stratocumulus spiraling around a central hub cloud. Overhead, fingers of cirrus moved cyclonically toward the low-pressure center. In the middle troposphere, Esther had a characteristic shield of altostratus cloudiness with base about 17,000 feet. The separate cirrostratus shield centered at about 50,000 feet. The cloud tops near the storm center extended above 50,000 feet. This is how the storm looked on the control ship's radar scope before the drop. Esther was a classic hurricane. Her symmetry was perfect. Her wall cloud, the white circular area, was 14 miles wide. Her eye, in the center of the wall cloud, was 15 miles in diameter. The Navy control ship penetrated the eye 3 times that morning to determine the best spot for the drop. The calm, quiet eye was surrounded by a high wall cloud where winds reached 120 knots and more. When the drop area was selected, the A-3D was loaded and fueled to fly into the hurricane. This is Esther shortly before the drop. As the A-3D and her crew neared the drop point, they had to dump 6,000 pounds of fuel to climb to 44,000 feet. The drop was made in the northeast quadrant. When the silver iodide mixed with the clouds, it caused the supercooled water to freeze and give up the heat of fusion. As shown on the control ship's radar scope, the eye started to fall away in the northeast quadrant and open up. The hurricane changed its course. In the wall cloud, 400 cubic miles had been converted to ice and snow from 45,000 feet down to 20,000 feet. The reconnaissance ship stayed with Esther to record the changes. Its mission accomplished, the A-3D, short on fuel, returned to base. The A-3D pilot gave his report.
Then he understood what we were going to do. He gave us a 5-second warning, and we dropped all 8 of the bombs on the outbound track. The true altitude of drop was 44,100 feet. True airspeed 470 knots, indicated airspeed fluctuating quite a bit because of turbulence, but it was between 220 and 230 knots.
The control ship remained in the hurricane, recording the changes. Esther's eye opened for about 2 hours. The eye began to reform into a figure 9 pattern. With the phenomenon observed and recorded, the control ship and other observation aircraft left the area. The Weather Bureau consultant, who had been aboard the control ship, gave the debriefing report.
And then the seeding occurred in this area that was about 15 miles wide. There had been a rather large weakness in the wall cloud. The wall cloud was probably 10, 15 or 20 miles wide. It looked something like this. Then the seeding occurred someplace in here. Before it was completely closed. Later on, there was a weak wall cloud down here.
Do you think this phenomenon was definitely due to the seeding operation?
Oh, you mean this?
Yes.
There's no doubt in my mind.
You have heard the Weather Bureau representatives say that by our method of seeding, we materially altered the cloud structure in Hurricane Esther. Now you may properly ask why we didn't go back and finish the job. Well, we just didn't have any more equipment. However, we're going back again with more. We're going to repeat the experiment several times, and if we obtain the same sort of results, we will know that we have passed a significant milestone on the road to taming hurricanes. Then we're going to go back and we're going to keep this up until we know how to do something about these storms.
What is that doing there?
It might seem out of place, a submarine-launched ballistic missile at an air weapons lab out in the middle of the desert. But China Lake played a significant role, a very secret for a very long time role, in the creation of the Polaris missile system and the nation's sea-based deterrent. China Lake engineering and warhead and propulsion and strategic studies formed a large part of the Polaris concept, moving away from the too large liquid-fueled Jupiter missile, the Air Force choice, to the smaller, solid-fueled Polaris, an all-around better concept, one that would actually fit in a submarine. The station also did the most comprehensive targeting study ever, which proved that smaller warheads on more accurate missiles would achieve the deterrence demanded by a deepening Cold War. China Lake's ability to project the advance of technology and apply that to a development program was also instrumental in Polaris breakthroughs, such as the integral reentry body warhead concept. And all this is aside from the propulsion improvement work, and the launch concept development and testing, and safety testing, and the massive motor testing program, which continued through Polaris and through Poseidon and Trident. China Lake's contributions to the Polaris concept and to the missile development program are some of its most significant accomplishments, and some of its least known.
As part of its atmospheric physics program, the Naval Weapons Center, in cooperation with the United States Air Force, is conducting major research into the dissipation of cold fog. Cold fog is a low-lying stratiform cloud composed of supercooled water and ice crystals, and whose temperature is 0 degrees centigrade or less. A series of tests were conducted at Elmendorf Air Force Base, Alaska, to determine best techniques and seeding materials to clear cold fog. 2 fog seeding concepts were explored. The first of these was the airborne dispensing of dry ice. The second was the dispensing of pyrotechnically generated silver iodide nuclei from the ground and from the air. Clearing was obtained almost equally well with both seeds. However, when logistics are considered, the pyrotechnic devices are superior. Briefly, the nuclei induce freezing of the supercooled liquid water drops. The resultant ice crystals grow rapidly and precipitate. This effects some clearing. As the ice crystals fall, coalescence occurs, which causes additional clearing. This series of still photographs, taken approximately 5 minutes apart, show the clearing effected. Note the sun pillar in the right center of the photograph, caused by the silver iodide-induced glaciation. Holes 4 miles long by 1 mile wide, large enough to permit aircraft operations, were cut in the fog. Some holes appeared as quickly as 15 minutes after seeding. Optimum visibility usually appeared in 1 hour. On the average, with low wind conditions, sealing and visibility remained high enough to permit aircraft operations for 2 hours. In general, while our results with fog clearing have not been spectacular, they have met or exceeded the short-term goals. We can modify moderately thick fog for short periods, long enough to permit aircraft operations. Additional research and testing should perfect the techniques and enable us to modify any fog, regardless of its thickness or location.
Weather modification is a weapon. It is a two-edged sword. The commander can use this weapon to improve his own situation or degrade the enemy either on a worldwide scale or in a local area. He can make the old maxims, fog-bound or mired in mud, become literally true. Thus, if natural weather phenomena can be altered, nature can be converted from a tyrannical master to a dutiful servant. While the current state of the art of weather control is far from achieving this ideal capability, impressive progress is being made. Understand that currently, the United States military has no operational weather modification capability. However, after 8 years of research and testing, we are close to having the wherewithal to develop one. Many other nations also are engaged in weather modification research. Let's see what we've accomplished so far and what, on evidence, appears to be feasible. Research and experimentation conducted by the Naval Weapons Center have been concentrated on 4 types of weather: warm and cold fog and warm and cold cumulus clouds. Since fog is either a low-lying stratus or radiation cloud, understand that the generic use of the term cloud in this film includes fog and cumulus. Warm clouds in this context, then, are defined as clouds whose temperatures are higher than 0 degrees centigrade. Conversely, the temperature of cold clouds is below 0 degrees. Experimentation so far proves that we can induce precipitation from cumulus clouds, and that we can dissipate certain types of fog over small areas. Beginning with these simple tasks, our ultimate goal is to develop techniques so that the United States can manipulate the weather whenever and wherever military requirements dictate. Research has demonstrated that seeding clouds with various chemical agents holds the best promise for successful weather modification. Currently, we are conducting tests with 2 types of seeding agents: hygroscopic solutions, seen here, and ice nuclei. These nuclei, which are used in cold cloud modification, are silver iodide particles released as pyrotechnic aerosol. This method is used because great numbers of very small nuclei are generated rapidly. The aerosol can be dispensed by specially designed burn-in-place fusees, by burn-in-place ground platforms, or by free-fall flares. This Naval Weapons Center developed flare unit, designated the WMU-1, is now ready for fleet delivery as part of a total weather modification subsystem. Research is underway to develop a rocket delivery system for use in violent storms or in disputed airspace. The secret, however, of successful weather modification is putting the proper seed in the exact place at the correct time. Over the past few years, we have conducted 25 major experiments throughout the world on fog and cumulus clouds to solve the specific problems of seed, place, time. Each summer for the past 3 years, clearing tests were conducted on coastal or advection fog at Arcata, California. The best results were obtained with a hygroscopic solution composed of urea and ammonium nitrate. These tests showed that within certain limits, we can dissipate advection fog, which is less than 1,000 feet thick, and if the wind is 10 knots or less. This capability is seen in a series of aerial photographs which show a VFR hole developing over the Arcata, California airport. The minutes indicate elapsed time from end of seeding. The beach line and a section of runway 13 and the beginnings of runway 19 are just visible. The whole is well developed, and details of the airport and beach line can be seen. After 65 minutes, the airport is BFR. Notice the complete clearing of the approach to runway 31. Our research into cumulus clouds takes several tacks. One is to induce precipitation, either rain or snow, in controlled amounts. Another is to control or divert hurricanes. We are also investigating weather modification techniques which will cause or intensify these storms. Let's explore briefly what's been discovered so far about cumulus clouds. The first to consider is warm cumulus. Limited experimentation was conducted over the Gulf of Mexico off the Texas coast to investigate techniques of artificially inducing precipitation. Clouds were seeded with hygroscopic solutions at their tops and at mid-level. All seeded clouds showed signs of modification, and from most, significant amounts of precipitation were observed. Adjacent clouds showed an accelerated rate of growth. In contrast to warm cumulus, our research into cold cumulus has been extensive. Results have been excellent, and seeding techniques are almost perfected. Precipitation experiments, conducted throughout much of the United States, have proven that pyrotechnically generated silver iodide nuclei are effective in causing precipitation at cloud levels where temperature is between -5 degrees centigrade and -10 degrees centigrade. Using this technique, precipitation can be induced nearly at will from suitable clouds. This technique has been demonstrated in overseas operational programs with varying degrees of success. In India, for example, a weather modification program began in late December 1966. The United States government offered to help alleviate a protracted drought and the resultant famine in the Bihar region of northern India. Because of the immediate need for water, a task force was organized quickly, and seeding operations began in February 1967. By virtue of the urgency of the situation and the paucity of suitable clouds at that time of year, any cloud that held promise for releasing precipitation was seeded. In all, during the next 2 months, some 100 individual target clouds were seeded, either with fusees or flares. On average, 1/4 to 1/2 inch of rain was released from half the clouds seeded. The total amount of rain induced in this program was not particularly impressive, nor was it enough to affect the drought substantially. However, overall results would have been dramatic if the seeding operations had been started 3 months earlier during the northeast monsoon, when water-laden, cold cumulus clouds abounded. These conditions were more nearly realized early in 1969, when we responded to an urgent appeal by the Philippine government for help in breaking a devastating drought which was crippling the economy of the nation. Using United States Air Force C-130s as seeder aircraft, silver iodide generating flares were fired into target clouds at their -5 degrees centigrade level, usually about 19,000 feet. Results were immediate and impressive. For instance, one seeded cloud system released 50,000 acre-feet of water in 6 hours. Another, on Cebu Island, released 12 inches of rain in an afternoon, filling a depleted reservoir. On average, however, rainfall from seeded clouds was 1/2 to 3 inches, enough to return the agrarian economy to normal. The potential for large area inundation realized by these seeding techniques has profound military significance in terms of immobilizing armor, infantry, and their logistical support. So far, we've discussed modification of individual clouds and relatively small cloud systems. Also under investigation is modification of large, cold cumulus storm systems, hurricanes, for example. To comprehend the magnitude of the problem and the staggering amount of energy involved, realize that a moderate strength hurricane in just one day releases as much energy as the total force of 400 20-megaton hydrogen bombs, enough to reduce the United States to rubble. Three hurricane abatement experiments were conducted in the Western Atlantic from 1961 to 1969. In each experiment, the right forward or northeast quadrant of the eye was seeded profusely. It was theorized that this would cause the eye to increase its diameter substantially and thus effect a reduction in wind velocity. Some temporary eye opening was observed, but no long-term modification was accomplished. However, the limited results of these experiments has led to an alternate approach directed towards modification of the rain bands, the spiral arms of massive cumulonimbus clouds. Accordingly, seeding experiments were run to determine best techniques for modifying cumulus cloud lines at sea, the building blocks of rain bands. The objectives were to make the clouds grow and thus expend their water vapor, either as cirrus or as precipitation. A secondary effect of precipitation is the cooling of the sea's surface. This reduces the available heat energy, the fuel source for hurricanes. These tests proved that the energy flow in cloud lines can be diverted by massively overseeding them with silver iodide ice nuclei. Extrapolating, it was reasoned that similar but more extensive seeding would cause like results in rain bands. Should this postulation prove to be true and seeding techniques perfected, artificial hurricane control could become a reality. The science of weather modification is at present far from exact. Accordingly, the two-edged sword is not yet within our grasp. A worldwide appraisal of other nations' weather modification capabilities indicates that the same sword is as yet also out of their reach.
Who was that?
Professor Charles C. Lauritsen was one of the people who actually created the China Lake Laboratory. Remembered as the desk-pounding scientist who led the way for making rockets a vital weapon, Charlie Lauritsen was one of the founders of KNOTS and an architect of the unique military-civilian team that made it work. A longtime Caltech professor and renowned scientist, Danish-born Lauritsen was instrumental in the general mobilization of American science to defeat the Axis. Not only was he the leading civilian scientist in the Navy rocket program, he was also a principal in the proximity fuse and guided missile projects, and even the race for the atomic bomb. His influence was key in China Lake's staffing with some of the finest scientists and technicians available, and in the station's post-war development. Charlie Lauritsen was a direct and driven man of great technical genius, one whose vision helped to shape China Lake's organization, its corporate culture, and its decades of success. A great deal more than just a name on a street sign or a laboratory marquee.
Most godforsaken place. This one little store and about 3 other buildings.
And my wife, her face fell, and she said, "Is this where we're going to live?" I said, "Well, I don't know, but that's what the sign says. It says NOTS on it."
I got into personnel, and they were running around with masks on their faces, and there were little piles of dust under all the windows. And it started to rain outside, and I thought, man, this is going to be kind of a wild place to bring my family up.
Described this to my wife as being a naval station down in something like Palm Springs in the desert. We arrived here in December from a year at Monterey, and the wind was blowing about 60 or 70 miles an hour and the temperature 20 degrees. And it persisted for a day or so, and the whole Palm Springs image got to be a little hard to support.
I asked Howie when I got here, this is a pretty bleak place, isn't it? He said, yep, pretty bleak. But it gets green in the summer, but you won't see much of that. You'll be in the lab.
Now, here's Peggy Small with the weekend weather.
Thank you, Bob. Well, you can get just about anything you want this weekend. How about a little rain? Mother-in-law coming? A little hail, perhaps. All you need are a few proper clouds, your airplane, a special silver iodide nuclei generator, and a little information, which I'll give you. What we're talking about is seeding cold cumulus clouds, clouds whose tops extend above the freezing level. You'll find either type A cumulus, a cloud in a low wind field, type B cumulus, a cloud in a wind shear where the wind velocity increases with altitude, or type C cloud, where the wind velocity actually decreases with the altitude. Now, the idea is to get the silver iodide from these nuclei generators into the part of the cloud where it'll do the most good. A sturdy aircraft, multi or single engine, capable of sustained operation at 25,000 feet is just the ticket. Carry supplemental oxygen, and be certain your plane has dual navigation communication gear. Dual automatic direction finders are handy items. So is an instrument landing system and a transponder. An instantaneous rate of climb meter is also useful, and make sure the gyro horizon and gyro compass are functioning properly. So that's the plane, and here's what you do with it. Based on the most recent meteorological predictions, anticipate the cumulus cloud growth through the freezing level in the target area. And time your takeoff so that you arrive on station at the optimum point of cloud development. It's better to reach the target cloud just as it's growing the most rapidly. Only clouds that are growing can be successfully seeded. Old clouds just collapse quickly. A growing type A cumulus will have a hard white top billowing upward. Find a white-topped cloud with a diameter of 1 mile or more, the minimum size for seeding. Seed tall clouds rather than flat clouds. Locate the -3 to -4 degree centigrade level, optimum for silver iodide nuclei. Set trim and power for level flight. While well away from the cloud, select a path which will lead you clear of other clouds. A good approach speed is 1 1/2 times the stall speed of the aircraft. Don't nose up as you approach the cloud. trust your instruments, and continue to fly attitude. Immediately outside the cloud, there's a downdraft, which quickly neutralizes. Turbulence increases until you get the hard upward jolt of the main updraft of smooth air. If the updraft exceeds 200 feet per second and holds for a few seconds, fire a round. The windscreen will pick up water. If water accumulation and the updraft lasts several seconds, fire another round. When exiting the cloud, you'll again hit the downdraft. A 90-degree, 270-degree maneuver will get you around to watch the seated tower develop. Usually, the volume of tower above the freezing level doubles within 5 minutes of seeding. If little growth occurs, seed the cloud tower again, unless it's dissipating or breaking off. But new towers or nearby clouds can be seeded immediately. By seeding rapidly growing new towers around a central mass, a single coherent cloud forms, and lots more precipitation occurs. Seeding an already vigorously growing cloud, or seeding at levels above -7 degrees centigrade, can produce a cumulonimbus. They're bad clouds. And remember, don't seed any downdrafts either, because the silver iodide is just wasted. Seeding the B, or wind shear cloud, is just a little different than seeding the A cloud. Rather than seeding the rising core, you seed the up shear towers. Where multiple towers exist, seed the most upwind tower of good seeding height. Again, look for hard white contrasty tops. To avoid embarrassment, enter the turret only at right angles to the wind shear. After seeding, you'll notice new towers developing just upwind from those you've just seeded. A third cloud type is a strange one, a monsoon cloud. The cloud leans upwind because the ground winds are stronger than the upper winds. The procedure is just the opposite from seeding a B cloud. Seed the most downwind tower that shows promise. With this basic difference, B and C clouds behave almost the same. Another technique is used when towers do not extend too far above the -4 degree level. These clouds can be seeded from the top. It's less precise and a little less effective, but it works. The whole schmear so far has been to get precipitation. Now, how to get rid of it. Let's say you have a developing cumulus congestus you want to get rid of. Seed the cloud in the updraft with several rounds, one every 3 seconds. The rapid growth causes the tops to break off and blow away. The base collapses and usually doesn't regenerate, and the precipitation stops. Isn't it fun to fool with Mother Nature?